Beyond the farthest galaxies, space seems to stretch without end, but what lies beyond the edge of the universe? Is there anything out there at all? Tonight, we'll explore one of the deepest mysteries in science. If you enjoy cosmic questions like this, please subscribe and share, and tell us in the comments, what do you think exists beyond the edge? Thank you for watching. Now, let's begin. He stands at the measurable limit of the cosmos, and lets the instruments speak first, because the edge of sight is not an opinion but a patient tally of light. The modern sky is a ledger filled by the Hubble Space Telescope, the James Webb Space Telescope radio arrays that listen like vast mechanical shells pressed to the night, and a small fleet of microwave observatories that capture the oldest light anyone can still receive. Together they map a boundary that is not a wall but a reach, the farthest distance from which signals have had time to arrive since space and time begin to expand. Astronomers call this distance the horizon, and like a sea horizon, it moves, as the traveller moves, always out there, always defined by time and speed and geometry, rather than by a ring of rock or an actual rim. The narrator considers how this horizon forms space itself, stretches and photons sail within that flow. In a young hot universe opaque to radiation, light cannot move freely, but as the plasma thins and cools, atoms form, and the fog lifts and the first free light escapes in every direction. That light shifted by expansion into microwaves fills the sky now, as a nearly uniform background. It turns the entire vault overhead into an ancient photograph, a single frame from a long story, a picture of a time when the cosmos is only a few 100,000 years old. By reading slight differences in temperature in that background, researchers infer the distribution of matter and motion very early on. The maps show a texture of tiny ripples that will later grow into galaxies and clusters, and the scale of those ripples, their broad sameness in every direction, hints that something very special happens in the first fraction of a moment. But the narrator keeps the pace measured and returns to the edge itself, because the first task is to describe what can be seen and what cannot. The visible universe is a sphere centered on the observer, a consequence not of privilege but of light travel time. Another observer in a galaxy a great distance away stands at the center of a different visible sphere. Both spheres include overlapping regions, and both exclude places the other can see. There is no single master bubble of sight, only many private horizons that move with their owners and grow as time passes. Yet this growth comes with a caveat. While time allows more distant shells to send their first signals, the continued expansion of space pushes far regions away so quickly that many messages will never arrive. There exists a second stricter boundary, called the event horizon of cosmology, which is the farthest distance from which light emitted now will ever reach the observer in the far future. The narrator introduces this idea gently, because it complicates the simple comfort that time reveals all things. If the expansion accelerates under the influence of a uniform energy that fills space, then beyond a certain range new light is forever lost to the outward rush. In that sense, the edge is dynamic, and double what can be seen now and what can ever be seen are not the same. The edge also depends on wavelength and patience. High-energy photons from violent early events are more likely to be scattered or absorbed before they can cross the thick first plasma. Low-energy radiation streams more freely, but it stretches until its wavelength makes detection difficult. Neutrinos, almost without interaction, leave an even older imprint that is now so cool and so thin that catching it becomes an act of exquisite craft. Gravitational waves, ripples of geometry itself, carry news from moments even closer to the beginning, but their signal is faint, and their measurement demands instruments that must be isolated from every earthly tremor and every thermal whisper. The narrator marks how each messenger opens a different window, and how every window frames a different edge. Then he steps closer to the philosophical trap and turns away from it, choosing clarity over speculation for now. The horizon is not a wall. It is not the perimeter of reality. It is the furthest distance at which the story has reached the observer, given the age of the universe and the way space stretches between all things. On today's sky, the shell of last scattering makes a grand backdrop, a mist of ancient photons that drift toward all observers at once. In front of that shell, within the last billions of years, galaxies condense and light up with starbirth. Their light reddens as space expands. Their rotation curves and lensing arcs tell of dark matter that outweighs the visible stars. Their distances whisper of a smooth, persistent acceleration that suggests an energy of empty space. Behind that shell, earlier than the first free light, the universe exists but cannot be seen by ordinary photons. The narrator explains that this is why the oldest ordinary picture ends there, and why more ancient clues must come from non-photon messengers, or from the imprint of early conditions upon the late-time sky. The measurable limit, therefore, is a layered surface, a limit of light, a limit of causality, a limit of future communication, and a limit of method. The instruments define those layers, and the layers define how the imagination may proceed without drifting too far from the ground. At this edge, a quiet tension gathers. Measurements of the background smoothness suggest that distant regions now causally disconnected once share information, as if early space expands so quickly that it smooths away roughness and stretches quantum seeds across enormous distances. Measurements of the pattern spectrum suggest that the early fluctuations are nearly scale invariant, a technical term that means similar structures appear on many sizes with only a gentle tilt. Measurements of the overall geometry suggest that on the biggest scales, space is very close to flat, not ballooned like a sphere nor saddled like hyperbolic space, and yet the precision leaves a small space for slight curvature that future instruments might resolve. Each of these clues stabilizes the picture of a large, old, expanding universe that begins hot and dense and cools with time. Each also nudges at something just beyond our reach, a process or condition that sets the initial state and then retreats behind the veil of an early epoch. The narrator remains careful. The edge doesn't force an answer, it simply enforces humility. A galaxy near the limit does not reveal its true age at the moment of emission, only the time the light has travelled and the changes the light has endured. The colour stretched by expansion speaks of distance and of time, but turning that colour into a precise yardstick demands a model for how the universe grows, and that model rests on independent checks that themselves trace back to the same background, and the same supernovae, and the same acoustic ripples frozen into the distribution of galaxies. Cross-checks reinforce confidence, yet they also remind us that all knowledge at this scale is drawn by inference from faint signals, accumulated over decades by teams that span continents, compared with simulations that fill supercomputers with colliding dark matter halos and cooling gas clouds, and then interpreted by a community that argues carefully, because small differences matter. The edge, therefore, is both a scientific structure and a social accomplishment. It is built by the National Aeronautics and Space Administration, and the European Space Agency, and the European Southern Observatory, and national observatories across the world. It is built by microwave satellites and balloon experiments, and ground arrays perched on dry plateaus and buried deep in polar ice. It is built by patience. And yet, even as the map grows sharper, the horizon does not become a wall. It remains a moving limit that expands with time and withdraws from certainty, with acceleration a boundary that both invites and denies. The section closes with the simple realization to ask what exists outside the edge of the universe. One must first understand that the edge is not outside anything. It is a radius of received information drawn by light and time, and by the quiet reach of human instruments into an ancient, ever-deepening night. He turns from the moving horizon to the faintest light, because that light is the oldest picture anyone can see. It comes not from stars or galaxies, but from a time before either exists, when the universe is a bright fluid of particles and radiation mixed so tightly that light cannot travel far without striking an electron. In that early crowd, every attempt at a photon's journey ends in a quick scatter, and the sky is a glowing fog. As the universe expands, it cools. When the temperature drops enough for free electrons to bind with protons, neutral atoms form, the fog clears, and light, at last, slips free to travel. That moment leaves a shell around every observer, a surface of last scattering that is not a wall but a memory. The photons from that surface flow in all directions and arrive here as a nearly uniform bath of microwave radiation spread across the sky. The narrator notes that the light is not perfectly uniform. It is almost the same in every direction, but not quite. Tiny differences in temperature and brightness. Parts in 100,000 pattern the whole sphere. These minute ripples seed the future, because where the light is a little cooler, matter is a little denser, and where matter is denser, gravity pulls a little harder, and in the long ages ahead those slight excesses grow into galaxies and clusters. To read these ripples, scientists build instruments that see in microwaves rather than in visible light. They fly observatories above the atmosphere. They float detectors on high balloons that drift in thin air, and they plant telescopes on high dry plateaus where the sky is clean and steady. They calibrate mirrors and receivers so carefully that a stray thermal sigh can mislead the result. They remove signals from our own galaxy, which glows in dust and magnetism, and from all the other galaxies whose radio whispers add a confusing mist. They check their maps by comparing different frequencies, different seasons, and independent instruments. Over decades, the picture sharpens. Space agencies release full sky maps that look like mottled ovals, each color a small tilt from an almost constant temperature. The narrator points out that these maps are not just pictures, they are measurements plotted on a sphere, then translated into a spectrum of angular sizes. The power in that spectrum is arranged in peaks and troughs, and those peaks tell a story about sound waves in the hot plasma of the early universe. Imagine matter and light bound together, compressing and rarefying like air in a bell. Gravity pulls inward, radiation pushes outward, and the competition sets up acoustic waves whose characteristic sizes imprint themselves on the sky we see now. The first peak gives the overall scale that corresponds to the largest sound waves that can complete a single cycle before the fog clears. The heights and positions of later peaks reveal how much ordinary matter exists, how much dark matter shapes the pull, and whether space on the larger scales is curved or flat. The results suggest a universe that is extremely close to flat, with only room for slight curvature that current data cannot decide. They also suggest that the fluctuations were seeded in a way that is almost but not perfectly the same at all sizes. On top of the temperature pattern sits another layer of information called polarization. When light scatters from electrons, it can become polarized, meaning its electric field prefers a direction. The arrangement of that polarization on the sky can be split into two general patterns. One pattern, often labeled with a letter that need not be spoken here, mostly arises from the same acoustic physics that sets the temperature peaks. The other pattern is twisted, and can be generated by gravitational waves moving through the young universe. Detecting that twisted pattern at the right scales would be a powerful hint that an early burst of inflation stretches quantum ripples of space-time into waves large enough to cross the sky. The narrator moves gently here because the measurement is delicate and the sky is complicated. Dust in the Milky Way can also produce polarized light that mimics a primordial signal. Careful subtraction and multi-frequency mapping are required, and the work continues with patience. Beyond the sky image itself, the faintest light ties together many other yardsticks. The same acoustic scale that leaves peaks in the microwave background also leaves a faint preference in the spacing of galaxies, a standard ruler frozen into the present-day distribution of matter. Observers measure that ruler by charting how galaxy clustering depends on distance, and then they compare it with the first sky map. Supernova observations add another chime to the same clock, revealing how the expansion rate changes with time. Together, these independent lines of evidence support a picture in which an early hot universe cools and grows dark matter, guides structure, and a smooth energy resembling the energy of empty space accelerates the expansion in later times. Yet the faintest light also carries puzzles. Its large-scale uniformity suggests that regions now too far apart to talk to one another were once close enough to share the same conditions. That suggestion motivates the idea of cosmic inflation, a brief early phase, when space itself expands much faster than any particle can move, smoothing out irregularities and stretching tiny quantum disturbances into seeds for all later structure. The overall tilt of the fluctuations, just a small deviation from exact sameness across sizes, matches many simple inflation models, but does not pick a favorite. The measured amplitude of the twisted polarization so far is small setting limits on how powerful the earliest gravitational waves might have been. The maps also show curious features that may or may not be accidents. There appears a region cooler than its surroundings, larger than one would normally expect by chance. There are alignments of low-order patterns that some analyses find suggestive and others find unremarkable once all uncertainties are considered. The narrator neither dismisses nor embraces these hints. He places them on a quiet shelf marked for future study. He then looks at the craft behind the certainty. To make these maps, teams must remove the motion of the Earth around the Sun, which imprints a large dipole pattern on the sky. They must correct for the motion of the solar system through the rest frame of the faintest light, which adds another very large dipole. They must calibrate beams, side lobes, and time response. They must subtract foregrounds that change with frequency and position. They must model noise that varies with time and temperature. They must design software to turn time-ordered data into maps and maps into spectra, and they must test those pipelines with synthetic skies to ensure that a signal is not invented by procedure. The trust in the faintest light is therefore earned by method, and the method leaves signatures of its own that can be checked by anyone with patience and access to the data. With those checks in place, the faintest light becomes the foundation stone for cosmology. It fixes the age of the universe to a precise range. It estimates the amount of ordinary matter and dark matter. It supports the case for a smooth late-time acceleration, and it points back toward an early process that sets initial conditions with great efficiency. Still, the narrator keeps wonder alive. This light is the outermost photograph, and like any photograph, it cannot show what happens before the shutter opens. Earlier than that, surface photons are trapped. If we want clues from those times, we must search for other messengers, such as a cosmic background of neutrinos so cool and thin that it is more a whisper than a breeze, or a background of gravitational waves, subtle enough to be confused with the tremors of a planet. Such searches are hard, but they are ongoing. Whether they succeed or not, the faintest light already sketches a clean outline that invites deeper questions. What powers the smoothing early expansion hinted by uniformity? What physics selects the small tilt in the pattern? Why do a few large-scale features refuse to sit perfectly within the neat framework? And finally, what lies beyond the last scattering surface, not in space but in time behind the fog, where photons cannot escape in epochs that can only be inferred? The section rests on this awareness. The faintest light is not only a picture of the deep past, it is a mirror that shows how much of the story is lost behind the early glow, and how far patience and ingenuity must go to reach beyond it. He measures the shape of everything with light as a ruler and gravity as a guide, because geometry at the larger scale is a question that only the sky can answer. The narrator begins with the simple picture: if space is perfectly flat, the paths of light are straight in the broad sense, and the sum of angles in a huge cosmic triangle equals 2 right angles. If space is positively curved like the surface of a sphere, light beams bend together, and the triangle's angles add to more than 2 right angles. If space is negatively curved like a saddle, light beams diverge and the angles add to less. No one can draw a triangle that large, but nature has drawn one for us, on the shell of the faintest light. The hot plasma of the young universe rings like a bell, and the size of its loudest note sets a standard length. When the fog clears, and that length is projected onto the sky, the apparent size of that feature becomes a geometric test. If the feature looks smaller than expected, the space between is curved one way. If it looks larger, the space is curved the other way. If it matches the flat prediction, geometry is close to Euclidean on cosmic scales. The full sky maps released by the Wilkinson Microwave Anisotropy Probe and later refined by the European Space Agency Planck mission find that the first and strongest acoustic peak appears at an angular scale almost exactly where a flat model would place it. The word almost is important. Measurement is never infinite. The instruments have finite beams, the foregrounds have complex textures, and noise is a companion that can be tamed but not eliminated. Even so, the confidence that large-scale space is close to flat grows as independent tests align. Galaxy redshift surveys trace a similar acoustic scale frozen into the pattern of galaxy, clustering a relic of those same early sound waves now stretched across billions of light years. By measuring the apparent size of that standard ruler at different depths, observers reconstruct how distances grow with time, and their results harmonize with the microwave sky. Weak gravitational lensing maps the small deflections of galaxy shapes by the web of dark matter. Those deflections depend on the geometry between us and the sources as well as on the mass that lies in between, and so in a careful analysis lensing becomes another voice in the choir. Supernova observations add their notes because the way the brightness of a standard candle falls off with distance also depends on curvature and expansion history. When the songs are layered, the melody points again to a universe that is very near flat with only a narrow margin left, for a slight bend that the current reach cannot decide. The narrator pauses to recall that flat does not mean simple. A sheet can be flat and still be finite if its edges meet in a way that causes space to wrap around itself. The name for this idea is cosmic topology. If the universe repeats, then light from a distant object might circle the cosmos and show the same galaxy in different directions, or might repeat the same large-scale pattern on the sky. Astronomers have searched the faintest light for matched circles, pairs of circular features that would be the same because the same region of space appears from 2 different directions. They have looked for periodicities in the distribution of galaxies that would whisper of a repeating hall. So far, the searchers find no compelling signature of such global repetition at sizes smaller than the visible region, which means that if space wraps, it does so on scales larger than all we can see. The narrator returns to curvature and the subtlety of inference. Curvature is encoded in the relation between distances and angles, but that relation is not a pure measurement of geometry alone. It folds together the matter content of the universe, the smooth energy that drives late acceleration, and the way the expansion rate changes with time. To extract curvature, observers must assume a physical model that links those ingredients. They prefer the simplest successful model that matches many different data sets, at once a model in which ordinary matter makes up a small fraction. Dark matter shapes structure, but does not shine, and a uniform energy component fills space and accelerates the late-time growth of distances. Against that foundation, the acoustic peaks the galaxy ruler, the lensing deflections and the supernova candles trace the same curves, and the best-fit geometry remains very close to flat. Yet the narrator does not let the result harden into doctrine. He notes a history of gentle tensions that appear and soften as methods improve or new measurements arrive. Some galaxy surveys and lensing projects have found slightly different strengths for the small-scale clumping of matter than what the faintest light would predict when extended forward under the simplest assumptions. Measurements of the present expansion rate using local distance ladders composed of variable stars and supernovae have sometimes differed from the rate inferred from the early sky under that same simple model. These differences may owe to hidden systematics or to statistical coincidence. They may also hint at subtle physics not yet written into the simplest picture. Geometry is entangled with all of this because a small tilt in one parameter can mimic a small curvature in another if the data are read through a narrow window. This is why cosmologists insist on joint fits that hold many rulers at once and on experiments that target complementary slices of the problem. The narrator then considers how gravitational lensing of the faintest light itself sharpens the story. As the oldest photons travel through the cosmic web, the clumps of matter they pass bend their paths and slightly smooth and twist the pattern imprinted at last scattering. By reconstructing this lensing effect, teams measure directly how matter is arranged along the line of sight and how geometry carries light. The lensing pattern measured by the European Space Agency Planck mission and by high-resolution ground telescopes agrees with the near-flat geometry and supports the broad inventory of matter and smooth energy. Still, even this elegant cross-check does not escape the reality that everything is linked. The interpretation of lensing depends on assumptions about the growth of structure, and that growth depends on the same ingredients tested elsewhere. Geometry growth and contents form a braided rope, and strength comes from the whole. From breadth, the narrator moves to scale. If space is extremely close to flat within the part, we can see that does not prove that the entire universe is flat everywhere. It could curve gently on scales larger than our horizon. It could be globally flat but finite through a topology too vast to reveal its repetitions. It could be one bubble of nearly flat space embedded in a larger inflating background where other bubbles curve in their own ways. The observable evidence cannot choose among those possibilities by itself. It sets limits and opens doors. The narrator holds to the contract set at the start, state the known. First, then open careful room for wonder. The known is this. On scales accessible to our instruments, the geometry is very near flat. The acoustic ruler, the galaxy ruler, the lensing twist and the candle ladder all sing a consistent tune that places our cosmic triangle close to Euclidean. The remaining uncertainties are small but not trivial, and they live where the sky is hardest at very large scales, very small signals, and in the joints where different data meet. The wonder follows. If the space beyond our horizon bends, the bend could be so slow that no experiment within any practical time can draw it. If space repeats the scale of repetition could be so grand that no matched circles can ever be found. If the flatness we see is the interior of a bubble, born from an inflationary storm, then the wall of that bubble lies beyond any light that can reach us. The narrator ends the section by returning to the human gesture that measures the shape of everything. It is a gesture of patience rather than conquest. A triangle is drawn across the oldest light with rulers made of sound waves and lenses etched by gravity, and the sum of its angles whispers that the grand stage on which all stories play appears flat across the whole theatre we can see. Whether the aisles that extend into darkness bend upward or downward remains a question for a future that may never fully arrive, and that very limit becomes part of the mystery we're trying to understand. He turns to the expanding fabric because what appears as the flight of galaxies is in truth the widening of the stage on which they stand. The narrator begins with a picture that is simple to state and careful to hold. In the nearby universe, light from other galaxies is stretched toward longer wavelengths. This reddening is not ordinary motion through space, but the mark of space itself, lengthening while the photon travels. Picture a web whose knots are galaxies bound by their own gravity, while the threads between the knots grow longer. The farther a photon must cross that web, the more the stretching accumulates, so colour becomes a quiet ledger of distance and time. Turning colour into history requires many rulers drawn from standard candles. The acoustic scale in galaxy spacing and the weak shearing of background shapes by the invisible web of matter. Together these checks say that the universe first slows under the pull of matter, and later speeds up under the push of a smooth energy that fills all of space. When that push dominates, distances between unbound structures grow ever faster, not because the structures hurry away, but because the room between them swells. The narrator lingers at a point that challenges common sense. Distant galaxies can recede faster than light without breaking the local speed limit of relativity, because the law governs motion through space, not the growth of space itself. Thus there exist regions that no signal can ever reach, not because of a wall, but because the sea between shores is rising too quickly to be crossed. This defines an event horizon for cosmology, the farthest distance from which a flash scent now can ever arrive. It differs from the simpler horizon that marks how far light has reached us since the beginning. Together they outline what can be known in principle and in practice. As acceleration quietly proceeds, galaxies slip beyond the event horizon. Their last light arrives, and then no more until only nearby islands remain in steady communication. Local bound systems resist the swell. Planetary systems, stars, galaxies and clusters keep their dances because binding forces hold them fast. Expansion is a large-scale behavior of distance across empty reaches. It does not disturb shelves or loosen the bonds inside an atom. Having separated local from global, he returns to the evidence for late acceleration. Surveys of standard candles show a gentle dimness at large distance, as if the light has travelled farther than a steadily slowing universe would allow. Galaxy maps reveal the frozen acoustic ruler at many depths, and its apparent size as a function of distance matches the same accelerated history. The detailed sky of the faintest light supports the same conclusion when its pattern is read through geometry and growth. The simplest account is a constant energy that never thins as space grows. The narrator follows a single photon born in a distant galaxy when the universe is young. With each passing billion years, its wavelength lengthens, not because the photon tires, but because the space between crests is stretched. The arrival rate of the crest slows as well, so that a brief burst in the galaxy's own frame lasts longer in hours. This time stretching is measured directly in the broad light curves of standard candles and in atomic lines that slide to the red, turning the reddening into a clock. Expansion, therefore, is not an abstraction, but a phenomenon that leaves marks in many independent ways. The story returns to the question of an edge. The edge is a record of what has reached us, not a fixed border beyond which nothing exists. As the late push grows, the share of the universe that can exchange signals with us shrinks in practice, even while time extends in principle. The future sky grows quieter, and the outer filaments fade beyond reach. That solitude deepens the mystery because any structures that lie beyond the event horizon are not only unseen now, they are unseeable ever. To consider them is to move from inference to conjecture. Yet the present evidence invites a careful step in that direction. The late push suggests a smooth energy active now at a gentle level. A similar idea magnified to a fierce intensity and acting for only a brief early moment would smooth the young cosmos, flatten its geometry, and stretch tiny quantum seeds into the pattern of ripples we now see on the oldest sky. Such an early inflationary episode would also enlarge a small patch into a region far larger than our visible domain, hiding whatever came before behind an ancient horizon. In that sense, the cosmos is bracketed by two limits of knowability, an early particle horizon that conceals the preluminous epoch, and a late event horizon that seals away most of the future. Between those limits stretches a corridor where evidence lives. Within that corridor, the expansion rate is the main character, and current work seeks to trace it with increasing precision. By measuring the acoustic ruler at a range of distances, teams reconstruct the growth of the scale factor without fixing a formula in advance. By mapping weak lensing, they track how structures grow. By tying nearby distance ladders to geometric anchors, they refine the present rate and test for slow drifts. The portrait that emerges is consistent from method to method, yet it is not without faint tensions. Some surveys prefer a slightly stronger or weaker clumping of matter than others. Some local measurements of the present rate differ modestly from the rate inferred by projecting the earlier sky forward. These differences may fade as calibration improves, foregrounds are better understood and selection effects are modelled with greater care. They may also be whispers of a richer story, in which the smooth energy evolves a little with time or gravity, departs a little from its familiar law across very large distances. Either way, the expanding fabric remains the quiet principle at work. He ends the section where he began on a widening stage. The lights of far cities drift outward, not because they rush along a highway, but because the highway itself lengthens beneath them. The closer lamps remain held by local ties, while the darkness between them rises like a tide. The edge becomes a moving ring of received news. It marks where the last waves from distant shores still find us, and it recedes as the sea swells. Beyond it, shores may continue without end, but their lanterns are carried away faster than any message can return to us. To ask what lies outside that ring is to stand calmly in the present and read the quiet handwriting of expansion across the sky, accepting that the same process that reveals the theatre to us also folds most of the world behind curtains of light and time. He turns toward the inflationary echo because the smoothness of the oldest light and the scale of its ripples call for an early episode that stretches space with astonishing speed. The narrator begins with the puzzle that first draws attention. Across the whole sky, the cosmic microwave background looks nearly the same in every direction. Regions that are now far apart and cannot have exchanged signals by the time the fog clears share almost identical temperatures, as if they coordinated their conditions beforehand. In a simple hot beginning without a special early phase, that sameness is difficult to arrange, because light and matter can influence only a limited neighborhood before atoms form and photons travel freely. Inflation proposes a remedy both bold and precise. If very early space expands by an enormous factor in a tiny sliver of time, then regions that were once close enough to share heat and information are blown far apart, and their common past becomes the reason their present looks so even. The narrator points out that this idea does more than wave at a problem. It predicts characteristic features that can be weighed. A violent stretch magnifies small quantum jitters in the energy and geometry of the young universe and imprints them as seeds. Those seeds should be almost but not exactly equal in strength across different sizes. They should be almost but not exactly arranged as a simple random field with a bell curve of fluctuations. They should be nearly the same in every direction, with only gentle tilts that match the details of how the early expansion slows and ends. Decades of maps of the faintest light reveal precisely such a pattern. The strength of the ripples changes slowly with size in a way that fits a broad class of inflationary histories. The statistical distribution is close to a bell curve. The arrangement is nearly the same on the whole sky. None of these alone would compel belief, but together they sketch the silhouette of an early stretch with convincing calm. He keeps the tone measured and notes that inflation also softens another old frustration, the question of large-scale geometry. Measurements show that the shape of space across the part we can see is extraordinarily close to flat. Without a special early phase, any small initial bend would grow or shrink with time, and it would be unlikely to find it tuned so near to zero today. A burst of dramatic growth pushes curvature towards zero, the way a taut pull flattens a rumpled sheet. After such a stretch, even a universe that begins with a modest curve looks flat when viewed within any region much smaller than the whole. In this sense, inflation supplies a natural reason for the near-Euclidean theatre on which the later drama of galaxies unfolds. The narrator then traces the physical sketch that most versions share. Some field with energy stored in its configuration behaves for a brief period like a uniform energy density that does not dilute as space grows. This drives an almost constant rate of expansion. As the field slides toward a lower energy state, the rapid growth ends, and the energy locked in the field reheats the universe into a hot, dense plasma setting, the stage for light elements to form and for the later release of the cosmic microwave background. Quantum fluctuations in both the field and the geometry are stretched to astronomical sizes during the burst. When the burst ends, those stretched ripples become variations in density and curvature that evolve under gravity into the galaxies and clusters we now survey. The narrator adds the most delicate messenger, the fossil tremor of gravity itself. If inflation occurs, quantum fluctuations of space-time become gravitational waves stretched across cosmic scales. Those waves leave a faint curl in the polarization of the oldest light, a twisted pattern, whose strength depends on how intense the early burst is. A strong early burst would leave a conspicuous curl, a gentle burst would leave a very small one. Many teams have searched cold skies from polar deserts and high plateaus with instruments tuned to this whisper. They observe at multiple frequencies to separate the primordial signal from the polarized glow of dust in our galaxy. They design analysis pipelines that test themselves on synthetic skies so that an eager algorithm does not mistake foregrounds for fossils. So far, the deepest maps have not revealed a clear primordial curl at the scales where inflation should speak the loudest, and that absence already tells a story. It sets an upper limit on the strength of the earliest gravitational waves and rules out simple versions in which the early stretch is extremely violent. The door remains open for gentler versions in which the curl is very small, perhaps beyond reach for a long time, yet still consistent with the other successes of the framework. The inflationary echo also changes how he imagines the unobservable beyond our horizon. In many versions of the theory, the burst is not a single event that ends everywhere at once, but a process that ends in some places while continuing elsewhere. Each region that finishes its burst heats up and becomes a universe with its own specifics. Our visible domain could be one bubble among many. If a neighbouring bubble once collided with ours near our past line of sight, it might have left a subtle mark on the faintest light, perhaps a broad circular feature or a gentle modulation across a large patch of the sky. A few reported anomalies have tempted such interpretations, including a region cooler than its surroundings and hints of alignments on the largest modes, but none has stood as a decisive fingerprint. Foreground statistical happenstance and the rough edges of analysis can all mimic faint patterns, and the narrator keeps them in a quiet box labelled maybe. He also considers alternatives with equal calm. Some proposals attempt to secure early uniformity and the right kind of seeds without an inflationary stretch. A slowly contracting phase followed by a bounce might, under special conditions, generate nearly scale-free fluctuations and wash away older irregularities. Other ideas change the behavior of horizons through modified interactions so that widely separated regions can still share information before atoms form. These constructions are clever and sometimes elegant, but they tend to struggle with side effects such as unwanted relics, unstable ingredients, or signals that do not line up cleanly with the temperature and polarization maps we already trust. The competition is not over, but the weight of present evidence keeps the inflationary story in front. Even so, the narrator refuses to let the framework harden into certainty. He lists questions that keep the field honest. What sets the initial state that allows the burst to begin? What stops the burst with just the right timing so that reheating is hot enough to make light elements, but not so violent that it erases the delicate pattern of seeds? Why is the tilt of the spectrum small but not zero, and why are the statistics so close to a bell curve? Could small departures from that simplicity hide in the data waiting for a sharper map? And what, if anything, surrounds the inflating patch? If inflation is eternal toward the future in other places, new bubbles might always be budding beyond our view, making our history one branch among uncounted branches. If inflation also arises from an earlier setting, we do not yet understand, then the burst that shapes our sky is itself a local chapter in a larger book. The narrator ends the section by returning to the echo we can actually read. The near-uniform sky, the almost scale-free pattern of small variations, the near-flat geometry and the present upper bounds on the primordial curl together form a coherent outline of an early stretch that sets the initial conditions with extraordinary efficiency. Gravity then works patiently for billions of years, turning tiny contrasts into the web of structure we now map from radio wavelengths to infrared light. The echo remains written across the whole vault as a soft mottling, whose statistics we can recite and whose origin we can model, even as the cause of the burst, its deeper context, and its ultimate connection to anything beyond our horizon remain open questions. In that open space the intrigue grows. An early wind smooths the sea, the ripples freeze into seeds, and the present sky carries their rhythm. What drives the wind and what lies beyond the calm water's edge are left for the next steps, where data invite mystery and the unknown begins to gather shape. He steps to the boundary and refuses to call it an end, because the horizon that wraps the visible sky is not a lid on reality, but a limit set by time and light. the narrator clarifies the picture with steady care. A horizon appears whenever signals require time to travel, and the messenger cannot outrun that cost. In the sea, the line where water meets sky moves with the sailor and yields to new views without ever becoming a wall. The cosmological horizon behaves in the same quiet way. It surrounds every observer as a sphere of received news, and its radius grows as light from farther shells completes its long crossing. But there is a second boundary that is different in character, the event horizon of cosmology, which marks the farthest places from which a message sent now can ever reach us in the far future. In a universe that accelerates that future boundary, tightens the reach of all future conversations, so that much of what exists already lies beyond any possible exchange. Between those two limits stretches a domain that contains all evidence and all inference, a corridor where maps can be drawn and tested. Beyond the visible sphere, however, the narrator holds a calm confidence that space continues. Nothing in the equations of the standard model of cosmology demands that reality stop where a vision stops. The geometry measured within our reach is smooth and nearly flat. The statistics of the faintest light look the same in every direction to a remarkable degree. The web of galaxies grows from a single set of rules that appear to hold everywhere we look. All of that regularity whispers that our patch is not chosen for special privilege. If conditions are typical, then the same rules may hold just beyond the horizon, and more of the same may extend outward without drama or edge. This is the simplest view, the continuation model. It does not require exotic structures or grand boundaries. It asks only that the patterns we see are not breaking exactly where we cannot test them. He acknowledges that simplicity is not certainty. The early inflationary burst supported by multiple lines of evidence stretches a small patch of nearly uniform space to a size vastly larger than our visible domain. That story leaves open the possibility that our patch is just one region in a broader inflating space where other regions complete their burst at other times, each becoming its own hot universe with its own local details. In that picture beyond the horizon, there are not only more of the same but also other domains that may differ in densities in the spectrum of primordial ripples, perhaps even in the values of constants that govern matter and light. Such differences would not be chosen by preference, but selected by the physics of how the early burst stops and how fields settle as reheating begins. If two such domains ever collide, the contact might leave a faint mark on the microwave sky, a broad, circular bruise or a gentle sweeping modulation. Searches for such imprints are ongoing, but evidence remains inconclusive. The narrator sets aside speculation that outruns discipline and returns to the practical question of how to know more about what lies just beyond the visible sphere. The first route is indirect continuity. If the patterns within the horizon are smooth across the largest scales we can measure, then a sudden change just past our limit would be unlikely. Cosmologists test this by measuring correlations in the faintest light, at the widest angles, by mapping galaxy, clustering across the largest volumes, and by reconstructing the deflection of light by the intervening web of matter. These measurements already enforce a quiet continuity. No vast discontinuity appears near the boundary of sight. The second route is lensing of the faintest light, which is sensitive to mass slightly beyond the surface of last scattering, because gravitational potentials along the path bend the oldest photons. That bending integrates information from just outside our visible sphere as well as from within it, offering a blurred hint of what lies beyond. The third route is to search for horizon-scale asymmetries, or preferred directions that would betray a spillover of influence from outside regions. Reports of such features exist, but they sit in a grey zone where the cosmic variance of a single sky, and the difficulty of removing foregrounds make firm statements hard. Future surveys that map polarization with greater precision and chart matter through weak lensing over most of the sky will tighten this net. The narrator also considers the idea of topology, in which space may wrap around itself on scales not much larger than we can see. If so, light could circle the universe and show repeated patterns or matched circles on the microwave sky. No such repetitions have been found down to current limits, which pushes any wrapping scale to well beyond our horizon. This absence again favours a simple continuation, but it leaves open the possibility that the repeat length is just too large. The question of nothingness beyond the edge never arises within these frameworks. There is no outer shell in the way a balloon has skin. Space does not embed in a larger room with air outside and a boundary to touch. The equations that govern expansion and curvature describe an interior geometry that is complete without a surrounding. When the narrator speaks of outside, he means beyond the region that can send signals to us within the age of the universe, not outside space in a literal sense. For that reason, he emphasizes language as carefully as he draws the maps. The edge is a temporal concept, a limit of light travel and causal connection, not a rim on an object. He imagines a galaxy that now sits well beyond our event horizon. Its stars burn and die, its planets turn, its own astronomers draw their own spheres of received news and ask the same question. Their answers do not include us because our light will never reach them, yet our absence from their knowledge does not change the fact that we exist. In the same way, the existence of unobservable regions is not downgraded by our inability to include them in our catalogue. What changes is only the method by which they can influence our inferences. Influence can come through initial conditions that still touch our sky, or through subtle correlations that reach to the edge and no farther. This is why the largest scale anomalies, however modest, draw interest. A slight cold region, a mild hemispheric power mismatch and alignment among the lowest order patterns. These may be statistical accidents or residue from incomplete foreground removal. They may also be casual footprints of processes that cross our boundary in the deep past. The discipline is to neither dismiss nor embrace them too quickly, to let new instruments test them with cleaner eyes. In parallel, theorists build models that could produce such features without spoiling the rest of the well-measured sky. The discipline continues in how the narrator frames hope. He does not promise that better technology will ever see beyond the particle horizon, because that is a wall built by the timing of last scattering, not by the quality of a mirror. He does not promise that any probe will send a message across the cosmological event horizon, because that would require overturning the very acceleration that the data now support. Instead, he points to ways in which more careful measurements within our reach can narrow the range of what is plausible beyond it. A sharper map of polarization can limit early gravitational waves, and so constrain inflationary stories that predict many domains. A deeper census of weak lensing can refine our matter lumps on the wider scales and test for unusual correlations. A longer record of standard rulers and standard candles can pin the expansion history more tightly, and test for gentle drifts that might hint at changing smooth energy. Through such work, the beyond remains present in the equations even when it is absent from the images. He ends with a quiet rephrasing of the section's theme. Beyond the horizon line there is not a cliff, but a continuation of law. In the simplest view, more galaxies, more filaments, more voids march outward, under the same rules we already read. In richer views, far domains with other details sit utterly beyond contact, their reality expressed only as boundary conditions written into our earlier sky. Between these poles lives the living practice of cosmology, which turns received news into maps and maps into questions. The horizon does not fence the universe, it fences our conversation with it. What exists outside is either more of the same or more of the possible, and both answers leave the night as open as when the question was first asked. He turns to the cold spot and other clues that live at the margins of certainty, because anomalies are where the map might begin to lift at the corners. The narrator starts with the sky of the cosmic microwave background, which, when cleaned of local dust and solar system motion, looks nearly uniform with the soft mottling of temperature differences. In that mottling, a broad, unusually cool region appears in one sector of the sky. It is not a sharp hole but a gentle extended basin that several teams have measured in independent maps. The odds that such a basin would appear by chance in a random sky end up being argued in papers and conferences because the answer depends on choices about how to define a feature, which parts of the sky to mask, and how to treat the fact that we can only observe one universe and therefore have only one roll of the cosmic dice. Some studies claim that the cool region is rare enough to raise eyebrows. Others find that once analysis choices are standardized, the surprise mostly softens. The narrator keeps the tone careful and turns from argument to possible origins. One suggestion is that the cold region could be linked to a very large underdense swath of matter along the line of sight, a supervoid that slightly robs passing photons of energy as the fabric of space changes while they cross it. Galaxy surveys have indeed found a dearth of galaxies broadly in that direction, a dip in the cosmic web rather than a hole, and that dip might push the temperature down a little. Yet detailed calculations suggest that the effect of such a void may be too small to account for the full depth and breadth of the observed basin, unless the void is stranger or the surrounding pattern more cooperative than standard models allow. His second suggestion reaches farther outward, imagining that our visible patch once brushes against another domain during an early inflationary epoch, leaving a circular bruise on the oldest light. The shape and scale of the cold region invite such dreams, but here too the balance of evidence remains undecided because foreground's instrument noise and the simple fact of chance can mimic broad circles as easily as deep causes can draw them. He steps beyond the cold basin to a family of wide-angle curiosities that cosmologists have weighed for years. On the largest angular scales, the strength of the lowest order temperature variations, the very broad swells called the quadrupole and the octopole look somewhat lower than naive expectations, and the planes that describe those swells seem to align with each other more than randomness would suggest. There is even a suggestive tilt that points vaguely near the plane of the Earth's orbit. Some call this alignment by a mischievous name and wonder whether residual local contamination, subtle data processing, or pure chance is at work. The European Space Agency Planck mission has revisited these questions with great care modelling and subtracting galactic emission across many frequencies and testing for biases in analysis pipelines. The overall conclusion is cautious. A mild deficit at the larger scales appears to be present relative to the simplest statistically isotropic model, and some alignments remain a little odd, but the significance is sensitive to choices, and no single anomaly rises to the level of a decisive discovery. The narrator notes another broad pattern, a hemispherical power asymmetry in which one half of the sky shows slightly stronger temperature variations than the other half on very large scales. This feature too lives in the zone where caution rules because it can emerge from chance in a single finite sky and lose its edge when different cuts or masks are applied. Still, its persistence across multiple data releases and instruments keeps interest alive and encourages theorists to ask whether a gentle modulation imprinted in the earliest conditions could tilt the sky this way without breaking everything else that works. Polarization adds another layer to the puzzle board. The preferred orientation of the microwave background's electric field carries information about the motion and density of the plasma at last scattering and about later gravitational deflections. On very large scales, the even pattern of polarization aligns well with expectations, while the odd twisted pattern remains faint within the current limits. This general success anchors the standard picture, yet the cold basin and the wide-angle curiosities ensure that the conversation does not go quiet. Each anomaly triggers proposed mechanisms. A local supervoid can induce a gentle cooling by altering the gravitational potential landscape through which ancient photons travel, but unless the void is extreme, the amplitude seems too low. A non-trivial global shape of space might in principle imprint matched circles or preferred alignments, but searches for repeating patterns and circles have found no convincing signals down to scales near the visible boundary, which pushes any wrapping out of reach. A brief early interaction with another domain might paint a circle or a hemispheric modulation, but identifying such a feature against the complicated foreground of our own galaxy and against the noise of a single sky remains brutally hard. The narrator keeps returning to method because in anomalies method is half the story. Building a map of the oldest light requires subtracting the bright glow of our own galaxy, which is rich in dust emission and polarized by magnetic fields. It requires correcting for the motion of the Earth around the Sun and the motion of the solar system through the frame, in which the background looks most uniform, because those motions imprint large patterns that must be removed with exquisite accuracy. It requires checking that an apparent cold region is not the ghost of a scanning pattern, a beam asymmetry or a stabilization algorithm that gently paints artificial shapes across the sky. It requires quantifying the confidence that a pattern is not a random flourish in a single realization of a random field. When all that is done, what remains must live in the shared space where different instruments at different frequencies in different seasons agree. Even then, judgment is careful. The narrator explains why careful attention to anomalies matters even when they remain tentative. The faintest light is our main fossil from a time we cannot otherwise access. If there are small dents or drifts in that fossil, they may carry information about the mechanism that smooths the early universe, about unexpected initial conditions, or about interactions across the edge of our visible region in an era when the young expansion is still shaping causality. At the same time, the sky is only one sample of a random process, and the eye is easily tempted to see shapes in the cloud. The discipline is to treat oddities neither as proof nor as error by default, but as places where the field must either improve its instruments or refine its expectations. He looks ahead with quiet specificity. Next generation surveys from balloon altitudes, polar deserts and high plateaus will map polarization with greater sensitivity over a larger fraction of the sky, which will help decide whether the hemispherical tilt and the broad alignments have counterparts in polarization that cannot be faked by temperature systematics. Galaxy surveys that trace the dark web through gravitational lensing and the three-dimensional distribution of galaxies will improve maps of large voids and clusters along the line of sight to the cold region, firming up or weakening the case for a local gravitational explanation. Cross-correlation studies that compare microwave maps with traces of structure at different distances will better measure how evolving potentials imprint late-time fingerprints on the oldest photons. Each of these steps tightens the weave of argument. The narrator closes with the right kind of suspense. The cold basin may end as a lesson in humility about statistics on a single sky, or it may sharpen into an actual relic of a structure or an encounter beyond ordinary expectations. The wide-angle alignments may wash away as foreground models improve, or they may persist in ways that demand a soft revision of early conditions. Either way, the anomalies have already served their purpose by driving instruments to cleaner designs and analyses to more transparent standards. In this calm pressure, the discipline advances. The great picture remains consistent and clear, yet at its edges the pattern ripples with small questions that refuse to flatten. Here the inquiry gathers strength because every mature map needs places where the ink thins and the paper shows through, inviting the next line, the next measurement, the next patient night under the sky that is almost uniform and yet just uneven enough to keep the mystery alive. He turns to the bubble universe hypothesis with the same steady care he applies to every daring idea, because if the early burst of inflation is not a single simultaneous event but a process that ends in patches, then reality may be quilted from many domains, rather than woven as a single endless cloth. The narrator begins with the logic that arises from success. Inflation explains the near uniformity of the oldest light, the near-flat geometry across our visible region, and the almost scale-free pattern of tiny seeds that later grow into galaxies. But many versions of inflation do not stop everywhere at once. Instead, the field that drives the early expansion slides down its energy landscape in a way that allows parts of space to complete the burst heat up and begin the ordinary history of particles and atoms, while other parts remain in the inflating state and continue to swell. In that picture, the inflating background does not end. It keeps creating new regions that finish their burst at different times. Each such region becomes a bubble of hot post-inflationary universe with its own local details set by how the field fell and how its energy became the first particles. Our visible cosmos could be one such bubble. The narrator holds the tone calm and then walks closer to the edges of the implication. If the energy landscape has many valleys, then different bubbles may emerge with slightly different rules carved into their matter. The average density after reheating may vary from place to place. The small pattern of seeds may have slightly different tilts. In more adventurous versions, even the effective strengths of forces or the masses of particles could differ if the fields that fix those values settle in distinct ways in different domains. Such variety is not added to the story for drama, but falls out of how fields can behave in a universe where quantum fluctuations jostle them while space stretches. The narrator keeps discipline and asks what the idea predicts that can be tested from inside one bubble. The most direct possibility is a scar from a collision. If while the inflating background still surrounds our young bubble, another bubble forms nearby and expands, the two expanding fronts might meet. The interaction can leave a broad feature on the surface of loss scattering, perhaps a circular or slightly elliptical imprint, a gentle step in temperature, or a shallow gradient across part of the sky. The imprint's size depends on the geometry of the meeting and on when it occurs relative to the time when the earliest light is released. Its contrast depends on the difference in conditions inside the two domains, and on the dynamics of the wall that briefly separates them. Searches for such circles and gradients have scanned the full sky maps from multiple missions. The results so far do not reveal an unambiguous collision. The strongest candidates either fade under stricter cleaning, blend into the expected statistics of a random sky, or coincide too closely with regions where foreground subtraction is difficult to trust. This absence does not erase the idea because many collisions would be rare or subtle, and the probability that our visible patch contains a clear scar might be low. Still, each tougher survey tightens the margin and forces models toward gentler differences, or towards separations large enough that most collisions occur beyond our view. Another possible sign is a shortfall or excess of large-scale power with a particular directional character, as if some distant event outside our horizon once nudged the initial conditions. Reports of hemispherical modulations and alignments have encouraged such talk, but here again the case remains open not because the features are absent, but because they sit where cosmic variance is large and where residual contamination can masquerade as signal. A third path to evidence lies in spatial curvature. In many inflationary models, a long-sustained burst drives the curvature towards zero so forcefully that any measurable deviation becomes unlikely. In a bubble scenario with a finite and perhaps not overly long inflationary period inside the bubble, a small negative curvature is sometimes expected like the interior of a saddle, though many models can still yield a geometry too flat to detect. Current measurements keep curvature very near zero with room for a slight bend, at a level that future lensing maps and deeper galaxy surveys may further restrict. Finding a definite small negative curvature would not prove the bubble story, but it would sit comfortably within versions of it, and would narrow the class of alternatives. The narrator then examines what happens at the meeting of domains, because the physics of the wall matters for both dynamics and signal. Between two regions that settle into different states there exists a transitional surface, with tension, a kind of membrane where the fields change value. As two bubbles expand and strike, that wall can ripple and shed energy into the surrounding plasma. Those ripples may seed a background of gravitational waves with a characteristic spectrum that depends on the speed of the collision and on the stiffness of the wall. Detecting such a background would be extraordinarily challenging, but it is among the few ways the idea might speak beyond the oldest light. Planned and imagined observatories that listen for long, wavelength gravitational waves could, in principle, constrain or someday hint at such features, though many mundane sources would crowd the same band. So the narrator keeps hope measured and returns to what can be said firmly. The bubble hypothesis is not a departure from the inflationary success, but an extension of it into a more global setting, one in which the early burst is generative over vast regions rather than singular and finished. It is not a uniquely required step by current data, but it is a natural possibility, and it draws interest because it provides a framework for understanding why our patch may be typical in some ways and special in others. Typicality would arise from the fact that many bubbles form so observers appear in many instances, while any special local features would arise from the particular value the fields take in our region. This way of speaking can drift toward questions about selection that belong to philosophy more than to measurement, and the narrator avoids such drift by keeping focus on concrete signatures. He also surveys sober objections. Some versions of eternal inflation struggle with how to define probabilities in an ever-growing background because if all possibilities occur infinitely, many times the ratio of outcomes can depend on how one counts. Some versions wander across a landscape of many states whose physical origin is not yet anchored by a complete testable theory. Some versions risk producing too many collisions or too many distortions of the oldest light, unless the inflating background persists long enough, or the energy differences between domains are small. These are not fatal blows, but they are reminders that the idea remains a live research program, rather than a finished map. He closes by returning to the question at the heart of this project. What exists outside the edge of the universe may be more of the same continuation without drama, or it may include other domains born from the same inflating background forever isolated by distance and by the late push of accelerated expansion. From within our bubble, the two possibilities can look very similar. The sky remains smooth, the ripples carry almost the same rhythm, the geometry sits very close to flat. Only faint hints placed at the broadest angles and the softest contrasts might distinguish one story from the other. In that space of almost sameness, the bubble hypothesis keeps its station respectable and bold, consistent with what is known, open to what may be found, and ready to be set aside if cleaner maps continue to show only a quiet sky. The narrator lets the thought rest as a balanced weight on the scale. Beyond our horizon there may be a single continuation or a garden of domains. The evidence today yields no verdict, but it grants permission to wonder, and it instructs where to look next in wide circles on the oldest light, in the tiniest bends of geometry, and in the faintest tremors of gravity that might carry across an unthinkable gulf the echo of an ancient meeting at the edge of a young world. He turns to the geometry of the infinite and finds that the word infinite hides more than one meaning, because space can be unbounded without being simple, and can be finite without possessing an edge. The narrator guides the thought carefully. In school, geometry, a flat plane extends forever, and a sphere encloses a finite area without a rim. In cosmology, the three-dimensional fabric can behave in analogous ways, but the possibilities multiply. A space can be globally flat yet folded so that a traveller who goes far enough in one direction returns from the opposite side like a game world whose screen wraps around. A space can be curved positively or negatively, and still be glued in patterns that make the whole finite while locally looking the same in every neighbourhood. The technical name for this family of ideas is topology, and it matters because it reframes the question of an edge. If space repeats, there is no outward boundary, there is only repetition, and the sense of beyond changes from further to again. The narrator pauses on the simplest construction that mathematicians use as a guide. Begin with a cube in ordinary three-dimensional space, and identify opposite faces so that crossing one face re-enters the cube from the opposite side. The result is a flat three-dimensional manifold that is finite in volume but has no edges. Every point sits in a region that looks Euclidean up close, and straight lines remain straight but paths eventually repeat. Light travelling through such a space can circle around and show the same object from different directions. On the sky of the oldest light, the last scattering surface may intersect itself and leave pairs of matching circles with identical patterns, because the same patch of early plasma is seen in multiple directions. This prediction gives astronomers a handle. Searches for matched circles across the microwave sky have been carried out with increasing skill. The absence of convincing pairs down to current sensitivity means that if space is wrapped, the repeating scale must be larger than the diameter of our visible region by a comfortable factor. That constraint does not eliminate the idea, but it pushes the repeat length outward so far that most practical effects vanish, and the wrapped space becomes observationally hard to distinguish from a simply infinite space that does not repeat. He steps from flat wrapped spaces to curved ones where the global structure can be richer still. A positively curved space can be finite in the way a spherical surface is finite, but three-dimensional analogues allow identifications that tile the whole with dodecahedra or other polyhedra, producing a universe that is globally closed without having a boundary. A negatively curved space can also be made compact through more intricate identifications, so that the local saddle shape does not imply that a traveller can drift forever without repeating. These constructions carry signatures similar in spirit to the flat-wrapped case, though their details differ. They tend to produce correlations on the largest angles that deviate gently from a perfectly random, statistically isotropic pattern. Some proposals have even tried to explain mild deficits of very large-scale power in the oldest light by suggesting a particular compact shape, but as data have improved, most specific topological claims have struggled to remain persuasive. The narrator keeps the emphasis on method. Beyond matched circles, there is a second way to test for repetition that uses the large-scale arrangement of galaxies as a kind of crystal. If the universe repeats, the pattern of separations between galaxies might show preferred distances, like the way diffraction peaks appear when light scatters from a regular lattice. In practice, however, the cosmic web is not a crystal, but a complex network sculpted by gravity and time, and the blurring effect of peculiar motions and selection functions makes clear lattice signatures difficult to detect. The result so far is again an absence of strong periodicities, which pushes any repeating scale to very large values. The narrator returns to the meaning of infinity in light of these absences. An unbounded space can be either simply connected like an endless Euclidean space that never repeats or multiply, connected like a flat torus that repeats, or a negatively curved compact space with complicated identifications. The data we have favor a geometry that is very close to flat and a topology that does not reveal repetition within the visible region. That leaves two broad options in practice. Either space is truly unbounded and non-repeating on all scales we will ever test, or space repeats but on scales so large that our sky contains only a single tile with no echoes. In both cases, the idea of an edge dissolves. There is no rim to strike, no outside to step into, only a continuity that either never closes or closes only beyond any light that can reach us. He also notes a subtler lesson. Topology and curvature become entangled with measurements of content and expansion. The apparent size of a feature on the oldest sky depends on the path light travels, which depends on both the local geometry and the global connectivity. A small amount of negative curvature can mimic or hide certain topological effects, while a wrapped flat space can disguise itself as a slightly curved unwrapped space if the repeating lengths are large. This is why joint analyses that combine the acoustic ruler on the sky, the acoustic ruler in galaxy clustering the weak lensing of distant shapes, and the brightness distances of standard candles are essential. Each probe knots a different strand of the braid, and only the whole rope carries weight. The narrator steps back to the philosophical temptation and sets it aside once more. The possibility that space repeats can invite imaginative images of one's own galaxy appearing in the sky like a faint cousin. But if the repeat length exceeds the diameter of the visible region by more than a factor of 2, such ghost images lie beyond reach. The search for matched circles already indicates that if such images exist at all, they are likely too large or too faint to see. This does not make the question empty. It resets it in a quiet key. We ask not whether we will ever fly around and return to the same place of origin, but whether the rules permit such a return in principle, and whether any imprint of that permission shows up in the fossil light. So far the sky answers with a modest no, within our reach, and a larger maybe beyond it. He turns to a final angle on the same theme, the relation between infinite and endless. An infinite space has unbounded volume, an endless space has no edges. A space can be endless and finite if it wraps. A space can be endless and infinite if it does not. Observations at present cannot discriminate between an endless finite cosmos of very large repeat length and an endless infinite cosmos that never repeats. What they can do is rule out small repeat lengths and sharp topologies that would paint circles or lattices within our horizon. That constraint, combined with the very near flatness of the measured geometry, leads to a picture in which the largest scales we see are already good approximations to the global shape, at least in the modest sense that no dramatic change appears just beyond the boundary of vision. The narrator ends the section by easing back to the central question of this work. What exists outside the edge becomes a different question when topology is considered. If space wraps, then there is no outside in a spatial sense, only further turns along paths that re-enter the same volume. If space does not wrap and extends without bound, then beyond the edge of sight lies more space of the same kind, potentially forever. In both cases, the word outside does not refer to a region beyond a wall, but to regions beyond our received news. The quiet implication is that the puzzle of the edge is not about a border at all, but about the global architecture that connects what we see to what we cannot. Whether the universe is a grand hall with walls too far to perceive, or an open plain with no walls at all, the night remains continuous, and the map we draw upon it is a local patch of a much larger floor. The difference between again and further may remain academic for a very long time, but even that distant distinction sharpens thought, and it teaches how to ask the question with precision and patience, which is how cosmology moves toward answers that never quite close the book. He turns to signals from nothing, and begins by defining nothing with care, because the vacuum of physics is not an empty stage, but a restless medium where fields occupy every point and cannot sit perfectly still. The narrator introduces a single quiet rule that drives the entire scene. In quantum theory, a field's value and its rate of change cannot both be fixed with absolute precision at the same time. This uncertainty, stated once and then held steady, means that even in the lowest energy state a field must tremble a little. Those tremors are called vacuum fluctuations. They are not particles rushing through space, but gentle jitters of the fields from which particles arise. In a tabletop world, these fluctuations reveal themselves as subtle shifts in atomic energy levels, and as a delicate force between closely spaced metal plates called the Casimir effect. In the sky they rise to an unimaginable scale, because the early universe takes those tiny jitters and stretches them into the seeds of everything large. The narrator links this quiet rule to the story told before. During the early burst of rapid expansion, the inflating space magnifies quantum ripples of the field that drives the burst and of the geometry itself. Modes that begin as microscopic waves are carried beyond the horizon of causal contact and frozen as gentle differences in density and curvature, like faint ripples preserved in cooling glass. Later, when the burst ends and the universe reheats, these preserved patterns become the initial map on which gravity works. Regions slightly denser pull a little harder, attract more matter and grow into galaxies and clusters. Regions slightly thinner thin further and become the great voids. The statistics of the faintest light preserve this origin story. The pattern of temperature differences across the sky is almost but not exactly the same at all sizes, as if a single process wrote a spectrum with a small tilt. The distribution of those differences is almost but not quite the shape expected from a simple random process. The near symmetry of the sky in all directions suggests that the mechanism operates uniformly. Each of these statements echoes the portrait of vacuum fluctuations gently stretched. He turns to the most elusive signature of all, the tremor of space-time itself. If quantum fluctuations touch the geometry, they can create a background of gravitational waves with wavelengths that dwarf entire galaxies. Such waves do not make sound, they tug distances. Their direct imprint on the oldest light would appear as a faint twisting pattern in the polarization, a curl that cannot be made by simple density variations alone. Detecting this curl would be a strong whisper from that early, almost nothing. So far, careful searchers have not found a clear primordial curl at the angular scales most sensitive to the burst's intensity. This absence becomes information. It tells us that if the early expansion happens, then it is likely gentler than the most exuberant models, leaving a very small gravitational tremor, consistent with the calm, nearly Gaussian statistics of the oldest sky. The narrator avoids symbols and keeps the meaning plain. Nearly Gaussian means that the temperature and polarization differences behave like a simple random field with only small allowed departures. Measurements have driven those departures toward very small values. That too supports the view that the seeds came from linear stretched fluctuations of a single slowly changing field, rather than from violent nonlinear processes that would have written bolder oddities into the sky. He then steps back to ask how a vacuum can hold energy at all. In the simplest picture, the energy of the vacuum is just the baseline against which all excitations are measured. But if that baseline is not exactly zero, it acts like a uniform energy spread through space, pushing the expansion to accelerate. The late-time acceleration we now observe can be described by such a uniform energy. Whether this is truly the vacuum's own energy, or the effect of a new field that is smoothly distributed, is an open question. Either way, the present push may be a cousin in concept, if not in scale, to the earlier burst that flung tiny jitters across the infant universe. The narrator refuses to turn this into metaphysics. He does not say that the universe begins from absolute nothing. The vacuum of quantum fields is a precise state inside a set of laws. If there is an origin for those laws, it lies beyond today's measurements. Instead, he focuses on what the laws we have already explained. They show how the smallest allowed uncertainties can be promoted by expansion into the largest cosmic structures. They show how the same mechanism can set the rhythm of temperature ripples in the oldest light, the list of peaks in its spectrum, and the near flatness of the geometry across the visible region. They even show how the lack of a strong twist in polarization becomes a measurement of how gentle the early burst must have been. He then places a mirror opposite that comfort. If vacuum fluctuations seed all things, then the details of what we see depend on which fluctuations happen in our patch. In a very large or multi-region universe, regions may differ subtly by chance, even if the same rules apply everywhere. This randomness does not undermine predictability. It shapes it. The theory predicts the pattern of probabilities and the size of typical differences. Observation reveals one sample drawn from that pattern. Cosmology becomes a science of controlled inference from a single drawn sky, with confidence rising as multiple independent relics repeat the same story. He returns to the laboratory for a moment, because a discipline that leans on enormous inference must also lean on small direct proofs. Energy level shifts in atoms, noise flaws in precision measurements, and the Casimir force between plates are terrestrial reflections of vacuum jitters. They confirm that the fields we place into the early story are not imaginary. They are the same fields that give atoms their structure and light its lines. The stretch from bench to cosmos is long, but it is continuous. The narrator traces another path through the same landscape by considering what might have gone differently. If the vacuum fluctuations had been strongly non-Gaussian, the sky would show a non-random pattern of hot and cold patches with preferred shapes. If the tilt of the spectrum had been large, small, or large scales, would have been very different from what we see. If the early gravitational tremor had been strong, the twisted polarization would already have stood out clearly. None of these hold. The sky sits close to the simple predictions of a gently rolling field expanded by a smooth burst. That closeness narrows the freedom of all models and has pushed the field over decades toward a small family of histories that agree with one another more than they disagree. The narrator then pivots to quiet questions that remain open. What sets the initial vacuum state, whose fluctuations are then stretched? Why does the early field move the way it does and stop when conditions are right for a hot plasma to emerge? Can later measurements of the smallest possible departures from Gaussian statistics or of the precise tilt pattern distinguish among remaining candidates? Could very long wavelength gravitational waves measured not in the sky's polarization, but in the stretch and squeeze of ancient light paths, ever be separated from the noise of a finite sky? Could a careful census of how structures assemble across time traced by weak gravitational lensing, and by the acoustic ruler in galaxy clustering reveal a subtle bend that forces an early change in the script? Each question remains within the practice of measurement. The narrator keeps the tone calm and repeats the core point once, then leaves it to rest. Signals from nothing do not tell a story of creation from absolute emptiness. They describe how a precise, restless vacuum inside a lawful universe writes faint statistical fingerprints that become, through patient expansion and gravity, the scaffolding of everything visible. The galaxies, the stars, the cold dust lanes, the sparse halos that wrap clusters, the weak lensing arcs that curve the shapes of distant hosts. The quiet dimming of standard candles across enormous distances all trace back to whispers of fields that could not be perfectly still. What lies beyond the edge where the continuation or a quilt of other domains is filtered through those same whispers, because the earliest fluctuations set the conditions at the horizon of our received news. In that sense, the outermost question is tied to the innermost tremor. If a vacuum can jitter, and if a great early swell can lift those jitters beyond contact and freeze them in place, then everything seen is a record of almost nothing made visible. He ends by letting the thought linger in the simplest language he can find. The smallest allowed restlessness becomes the largest known structure when space stretches it and gravity grows it. The sky is a fossil of that transformation, calm and mottled, precise and suggestive. The next steps are already clear, sharpen polarization maps. Expand lensing surveys, extend the rulers of galaxies, and keep listening for the quiet twist that would turn a careful inference into a full confession from the earliest time we can never directly see. He turns to higher dimensions and hidden realms with the same steady voice he has used for horizons and echoes, because proposals that add unseen directions promise to explain why gravity is so gentle, and why the early burst unfolds as it does, yet they must speak through careful predictions or remain quiet speculation. The narrator begins with a picture that is simple to imagine and hard to test. Everyday experience suggests 3 spatial directions and 1 time direction. The laws that guide particles and light can be written in that 4-dimensional language, and they work with exquisite accuracy across laboratories and galaxies. Still, the mathematics of unification has long hinted that a deeper description may require more spatial directions curled so small or shaped so subtly that ordinary life cannot sense them. In some constructions, the familiar particles arise as vibrations of tiny strings, whose allowed notes depend on how extra dimensions are folded. In others, our visible universe sits on a membrane, a brain floating within a larger space that has more directions than we see. In both cases, the unseen geometry affects what kinds of particles and forces can exist, and it may change how gravity spreads. The narrator turns to gravity first because gravity is different from the other forces. It is both universal and weak. A single magnet can lift a paperclip against the entire Earth's pull, yet the same pull sculpts stars, binds galaxies, and bends the paths of light across clusters. One way to understand this great range is to imagine that gravity can leak into extra dimensions, while the other forces are confined to the brain we inhabit. If gravity spreads into a larger volume than the other forces do, its strength within our 3-dimensional sheet would be diluted. This idea leads to tests that can be performed. If extra dimensions are large compared with the tiny scales probed in precision experiments, gravity might deviate from its familiar inverse square behavior at very short distances. Ingenious tabletop experiments with torsion balances and microfabricated oscillators have pushed the search for such deviations down to fractions of a millimeter. So far, the inverse square law holds, which places tight limits on how large extra dimensions could be if they exist. If the extra dimensions are small or warped, they might reveal themselves through new resonances or missing energy in high-energy collisions, as if particles sometimes disappear into the bulk or return as excitations associated with the geometry of the hidden directions. Particle colliders have searched for such signs and have not yet found them, which shapes the space of viable models rather than closing it. Brain settings offer another path from geometry to observation. If our universe is a brain inside a higher dimensional bulk, then gravitational waves can travel in the bulk as well as along the brain. The way those waves propagate might change their dispersion, or cause subtle leaks of energy, potentially altering the strength or the timing of signals from distant collisions of compact stars. The current catalogue of gravitational wave events is still young, but as it grows, careful studies of waveforms and arrival times will test whether gravity behaves exactly as expected over vast distances or shows trace signatures of extra corridors in which it can move. Cosmology also enters this conversation because the early burst of inflation and the later smooth acceleration can be described in brain language. In some scenarios, the field that drives the early expansion is a measure of the distance between brains, and the end of inflation occurs when those brains meet. In others, the accelerated expansion arises not from a uniform energy within the brain, but from the curvature of the bulk and the way it guides the brain's motion. These pictures are elegant in outline, but the narrator keeps his promise to favour clarity over flourish. They must reduce to the well-tested successes of the standard cosmology. They must reproduce the near-flat geometry and the almost scale-free seeds, and they must not introduce unwanted relics or distortions that the oldest sky would have revealed. Some versions manage this at least in broad strokes, while others struggle with instabilities or with predictions that overshoot what the maps allow. He moves next to the idea that higher dimensions might host other brains on which other universes live, separated from ours by an imperceptible gap in a direction we cannot access. In such a layered cosmos, the phrase outside the edge changes its meaning again. What lies outside our horizon in the familiar three directions could be more of the same space, yet in directions orthogonal to all of them. There could be other brains with their own matter and light. Interactions between brains would be limited. Only gravity and perhaps very weak exotic messengers would connect them. If two brains passed near each other in the bulk, their gravitational fields could imprint subtle signatures upon each other. A close approach might conceivably seed a pattern in primordial fluctuations or generate a burst of gravitational waves. Such events would be rare and model-dependent, and the search for their footprints merges with the broader hunt for anomalies in the oldest light and in the background of gravitational waves. The narrator then considers whether extra dimensions could help explain the values of the constants that shape chemistry and life. If the sizes or shapes of hidden directions control the frequencies of string vibrations, or the effective couplings of fields, then small shifts in geometry could select different physics in different regions of a larger space. This idea leans toward a landscape of possibilities, where many vacuum states exist and different brains or different domains within a brain explore different points in that landscape. In such a setting, what exists outside might be another patch where the constants are slightly different, and our patch is simply one where structures and long-lived stars arise often enough for observers to appear. The narrator refuses to chase selection arguments. He acknowledges that the idea gives a language for variety, but he anchors again in measurement. If geometry selects rules, then it also selects signatures. The primordial spectrum should keep the gentle tilt we already see. The near-Gaussian statistics should remain near-Gaussian. The near-flat geometry should remain near-flat. Any departures must be small and crisp enough to rise above the noise of a finite sky and the fog of foregrounds. Until such departures stand firmly higher, dimensions remain a graceful scaffolding that may support the house we already inhabit, rather than a new house of their own. He returns to gravity once more, because gravity has become a messenger we can finally hear directly. If higher dimensions exist, some models predict a very slight loss of amplitude for waves that travel cosmological distances as if a tiny fraction of their energy bleeds into the bulk. Others predict additional polarization states or tiny echoes following major events. The current instruments have not resolved such features, but planned observatories on the ground and in space will deepen the listen. In parallel maps of weak gravitational lensing over most of the sky, we'll test how gravity pulls across the larger scales, constraining modifications that often accompany higher dimensional frameworks. The narrator ends the section by returning to the quiet promise that motivates these ideas. Higher dimensions offer a way to weld disparate parts of physics into a common geometry, to treat particles as notes played on an instrument whose shape includes directions we cannot walk. They offer mechanisms for a gentle gravity in a natural early burst, and they offer new spaces where other brains and perhaps other universes could reside without ever touching our light. But they also carry a discipline. They must lean down into the world we measure and leave fingerprints that can be seen in colliders, in torsion balances, in gravitational waves in the oldest light, and in the assembly of structure across time. Until those fingerprints are clear, the hidden realms remain a plausible architecture behind familiar walls. Beyond our edge may lie nothing more exotic than more galaxies along familiar axes, or it may include orthogonal corridors in which other brains drift in a bulk that our senses cannot address. The question remains open, and the method remains the same. Hold the laws we know, extend them carefully, and listen for small decisive consequences. In this way, higher dimensions do not replace the sky we see. They thicken it, turning the canvas into a layered fabric where the visible thread is only one strip in a broader weave. The night looks the same, either way calm and precise, while beneath it the possibilities quietly multiply, waiting for a trace that will turn suggestion into map. He turns to the landscape of other laws and keeps his step unhurried, because the notion that physics might take different forms in other domains is as delicate as it is grand. The narrator begins with what appears steady inside our sky. The strength of electromagnetism, the ratio of the proton mass to the electron mass, the charges that define how particles speak to fields, the pace at which certain isotopes decay, and the gentle energy that drives late-time acceleration, all seem constant within the precision of current instruments. Light from distant quasars threads through cool clouds and arrives as patterns of atomic and molecular lines whose relative spacings match those measured on Earth. Natural nuclear reactors that once flickered in ancient rock-leave isotope ratios that align with the same rules we use today. Atomic clocks compared for years refused to drift apart by more than the tiniest allowable whispers. The oldest light across the whole sky is described by a single set of parameters that fit temperature polarization and the subtle smoothing introduced by gravitational lensing. This steadiness does not seal the question, it frames it. From within that frame, he asks what it would mean for other regions to cool into slightly different rules. If the early burst of inflation buds many bubbles from a wider inflating background, and if the fields that determine forces and masses can settle into more than one low-energy state, then some far domains may carry slightly altered constants. A small change in the strength of electromagnetism would shift how tightly electrons bind to nuclei, thereby moving the energies of chemical reactions and the balance by which stars ignite and live. A small change in the ratio of proton mass to electron mass would shift vibrational ladders in molecules and the paths by which cooling gas finds its way into stars. A small change in the smooth energy would alter when and whether galaxies condense before the expansion runs away. He resists the temptation to turn this into a catalogue of worlds and keeps the focus on measurement. If variation exists, it must first be sought in the light we already hold. The absorption lines of distant gas provide a long lever arm. If the strength of electromagnetism differs slightly across space or time, the fine pattern of certain doublets will shift relative to others. If the mass ratio drifts, molecular lines will slide differently than atomic lines. If the smooth energy is not exactly constant, the relation between apparent brightness and distance for standard candles and the apparent size of the acoustic ruler frozen into the galaxy, Webb will deviate from the simple curve drawn by a constant push. Observers have searched along these avenues. Some analyses have reported hints of gentle gradients in the strength of electromagnetism across the sky, when certain quasar samples are arranged in particular ways, but other teams with different samples and calibrations have not seen those hints persist. Molecular spectra from distant absorbers continue to agree to tight tolerances with laboratory values. Measurements of the geometry and growth of structure remain consistent within small uncertainties, with a smooth energy that does not evolve visibly over the redshift range we can test. The narrator treats these results as lessons in method rather than as final verdicts. Precision spectroscopy must negotiate instrumental quirks, wavelength calibrations, and blends of lines in crowded regions. Distance ladders must tie local rungs to geometric anchors and carry their uncertainties honestly across great spans. Galaxy surveys must measure redshifts and selection functions cleanly enough to trace the subtle acoustic preference in separations. Weak lensing maps must turn small biased shapes into unbiased measures of the invisible web. When these disciplines converge and find no drift, the absence itself becomes information. Large departures are unlikely, and any real differences must be small. He then asks what kind of small differences would still leave a sky like ours. The answer is narrow. Increase the strength of electromagnetism too much, and atoms hold together so tightly that chemistry becomes rigid. Decrease it too much, and atoms are loosely bound molecules unstable, and cooling inefficient. Change the ratio of proton mass to electron mass too much, and the energies of molecular lines move in ways that frustrate the loss of heat needed for clouds to collapse. Make the smooth energy much larger and structures never grow. Make it negative and the universe may recollapse before long-lived stars can form. Between these cliffs lies a corridor where the constants sit at values that allow hydrogen to make helium stars to light and heavy elements to assemble in patient cycles of birth and death. Our measurements put us within that corridor. The landscape idea says there may be other corridors, other plateaus and other ravines, and that different regions may occupy different points upon them. He does not decorate this suggestion with philosophy. He simply notes that frameworks which already help elsewhere make such variety plausible. The shape and size of any hidden dimensions, if they exist, could control the allowed notes of the fields, and so fix the couplings we treat as constants. The number of low-energy basins available to the vacuum, if more than one exists, could allow different regions to settle into different basins when the early burst ends. If so, what lies outside our horizon might include domains where a few constants are shifted by small steps, while many others remain the same because the same underlying structure limits how far they can wander. He then turns back to the narrow ways that observation could reveal difference, without seeing the domains themselves. One path is a convincing detection of position-dependent changes in well-chosen line ratios in quasar absorption systems, repeated by independent groups across many telescopes, and cross-checked with different atoms and molecules that respond differently to the constants. Another path is a shallow scale-dependent departure in the acoustic ruler as a function of distance matched by a corresponding departure in standardized candle curves, pointing to a gentle drift of the smooth energy. A third path is a careful census of the earlier star formation in pristine gas, where the cooling routes depend sensitively on molecular physics, a mismatch between predicted and observed metal. Free stellar remnants could mark a slight change in the rules that govern those routes. Each path is difficult, many confounders stand in the way, and no single sign would suffice. A web of consistent independent hints would be required. He also keeps the inverse point in view. The longer the sky holds to a single set of constants across time and direction, the tighter the leash on any landscape. If no drifts are seen in ever cleaner spectra, if no evolution in smooth energy is detected by ever larger surveys, if clocks continue to agree within ever smaller bounds, then any variety must be confined beyond our horizon and beyond our sensitivity, and the continuation picture gains quiet strength. The section closes by returning to the question that threads through all others. What exists outside the edge of the universe may be more of the same, drawn without change by the same laws on larger and larger scales, or it may include far domains where a few numbers take slightly different values and write slightly different stories in matter and light. Within our horizon, the constants behave like faithful metronomes keeping time for stars and chemistry, with a steadiness that gives prediction its power. If other beats exist, they are faint enough that our best instruments do not hear them yet. That silence is not empty. It is a measurement. It says that either the score is universal across the part of the stage we can test, or the variations lie far beyond the ring of received news. Between those possibilities, cosmology proceeds as it always does by tightening rulers, cooling detectors, lengthening baselines, and letting the sky decide. In that patient practice, the landscape becomes not a catalogue of fantastical worlds, but a disciplined question about whether the rules we trust are local or global, and whether the calm order we see is the only way a universe can be, or simply the way our patch has chosen to be. He turns to the search for leakage, the quiet program that asks whether any messenger inside our horizon carries fingerprints from beyond it, and he keeps the tone steady because the signals, if they exist, must be small. The narrator begins with light that is older than galaxies, and was the way its polarization could twist. When the faintest light last scatters, its electric field tends to prefer directions set by local motion and density, building an orderly pattern. Gravity later deflects those photons and smudges that order a little, but the basic even pattern remains. If something tilts the polarization orientation as the waves cross the deep, the sky would show a tiny rotation that mixes the even and the odd patterns in a way that ordinary physics does not. This effect, often called cosmic birefringence, would act like a pane of glass that turns polarization by the smallest of angles. Some teams reading the European Space Agency maps have reported hints of such a rotation at the level of a small fraction of a degree, while others with different calibrations and cross-checks find that the signal dissolves within uncertainties. The narrator does not lean either way. He notes that a true rotation of this kind could come from a light field that permeates space, or from parity-breaking physics tied to the origin of the earliest ripples, or more prosaically from minute errors in how instruments set their own polarization reference. The cure is cleaner maps, more frequencies-independent detectors and sky patches where dust is thin. He then turns to a second kind of leak, the one that gravity itself might carry. Gravitational waves travel through everything with almost no loss. If the early universe hosts processes that shake the fabric of space, the result is a background of waves that arrives from all directions like a sea swell. If other domains once met ours, or if the fields that end the early burst briefly undergo a violent phase change, the background might include a faint bump at a characteristic wavelength. Ground interferometers already listen for high-pitch waves from colliding compact objects and for a broad noise that could hide a cosmic contribution. Pulsar timing arrays listen for waves so long that a single cycle can take years, sensing them through tiny changes in the arrival times of pulses from millisecond clocks scattered across the sky. Both approaches are advancing. What matters for leakage is not just whether a background exists, but whether its spectrum or its sky pattern carries a shape that cannot be explained by ordinary astrophysical sources alone. A purely isotropic hum with a slope set by black hole, pairs merging in galaxies is expected. A deviation from that slope, or a pattern that prefers a direction or a colour, would raise other possibilities. The narrator keeps the language close to the ground. Patterns on a single sky are subtle, and more data are required to argue beyond enthusiasm. He walks next to the oldest light again, but now with ears for parity. Ordinary density ripples make even temperature patterns and even polarization patterns that do not mix in forbidden ways. A universe that violates parity even just a little could imprint odd combinations that are usually zero. Instruments therefore search the cross terms that in the standard picture should vanish, looking for an imbalance that could hint at a twist in physics or at a gentle push from outside our visible patch in the primordial past. So far, those cross terms lie near zero within present errors. That near zero already rules out many flamboyant ideas and leaves standing only models where any parity breaking is slight, or where nature keeps its oddness in bands of the spectrum we have not yet measured with enough precision. He adds a different class of leakage that lives not in patterns but in spectra. If the young plasma is not perfectly uniform or perfectly thermal, the faintest light would not be a perfect blackbody. Very early energy injections, such as the decay of exotic particles or small departures in how the early burst shuts off, could imprint gentle distortions of two main types. One kind changes the brightness at high frequencies by a tiny amount. Another kind spreads or gathers brightness in a way that leaves a different signature. The measurements by a space instrument in the 1990s already set astonishingly tight limits on any such distortion, showing that the sky is an almost perfect blackbody. Yet there is room far below those first limits for small signals that new instruments might reach. A detection of a clean spectral distortion with the right shape would be a strong clue to physics that leaks into our sky from times earlier than the last scattering of ordinary light. The narrator shifts to matter that is not luminous and asks whether its pull can betray news from beyond. Weak gravitational lensing maps trace how the invisible web bends light from far galaxies. If the largest scale pattern of that web shows a mild drift in strength or direction that cannot be explained by known systematics, it could hint at an early modulation across our patch, perhaps a leftover from a contact with something outside before the last scattering surface forms. Present surveys already tie the late growth of the web to the same smooth acceleration that distance ladders and acoustic rulers infer. Future surveys that map almost the entire sky will be able to test for gentle hemispheric differences with far greater care. Alongside lensing sits a cousin, the late integrated Sachs-Wolf effect, in which the steady outward push of the smooth energy lets ancient photons gain or lose a little energy as they pass through evolving gravitational wells and hills. By cross-correlating maps of the faintest light with maps of galaxies at different distances, observers can detect this effect. Slight anomalies in that correlation could hint at unusual changes in the large-scale potential field, again raising the possibility of an early tilt. Current measurements mostly support the expected signal, but their errors at the larger scales are still wide. The narrator walks to the cosmic radio dipole with equal restraint. Our motion relative to the frame in which the faintest light is most uniform produces a strong dipole pattern in that light which acts as a check on calibrations. If radio source counts at large scales share the same dipole, their alignment and amplitude can test whether there is an extra cosmological dipole beyond our motion. Some catalogues have hinted at mild mismatches, but systematics in source selection and flux calibration across the sky complicate the reading. New radio surveys with uniform coverage will improve this test. He then looks at the night through a different window, the line from neutral hydrogen that glows at a single radio wavelength in its rest frame and is stretched by expansion into a long band. Mapping that line across large volumes either by summing its glow from many unresolved sources or by imaging sharp structures at high redshift could reveal the first structures rising from the dark. A global absorption feature that is unusually deep or oddly timed could hint at new interactions or a surprising background. A power spectrum that deviates in shape from expectations could hint at a large-scale modulation of initial conditions. Early reports of surprising depths have already taught the field how unforgiving foregrounds and instrument environments can be. A new generation of arrays and perhaps a telescope on the far side of the Moon may settle these questions, and with them the chance that very early physics leaves a crisp signature in the radio dawn. The narrator returns to supernovae and standard candles for one more check, because leaks might tilt the expansion, not by adding a new component, but by slipping a directional preference into the late time push. If the acceleration were slightly faster in one direction than another, distant candles could appear a little dimmer on one side of the sky and a little brighter on the other. Current compilations constrain any such dipole tightly, and any remaining space for it is small. The symmetry of late-time acceleration within our horizon therefore stands as a calm statement. If there is leakage, it does not shout, it whispers. He closes with the method that binds all these searches. No single odd hint counts. A rotation in polarization must be confirmed independently by instruments with different systematics, and must be matched by the expected mixing of patterns across scales. A background of gravitational waves must show a spectrum and a sky pattern that distinguishes early cosmology from the chorus of astrophysical mergers. A spectral distortion must carry the clear shape that only certain early injections can create. A hemispheric modulation must appear in temperature polarization and lensing in a way that rescues it from the charge of chance. Only a web of consistent repeated cross-checked clues can be called leakage. Until then, the ski remains mostly faithful to the simplest story. That faithfulness is not a disappointment. It is a map of where the improbable must hide. The search continues along many quiet paths, because beyond our horizon, any influence must be subtle, written into the initial conditions or into the faint tremors that still roam the dark. The night offers no promises, only patient tests. If something presses upon our patch from a larger reality, its pressure will reveal itself as a small but coherent deviation, repeated across different messengers. If nothing presses, then the lack of leakage is itself a lesson. telling us that whatever lies outside, whether continuation or other domains, holds to a boundary that is causal and clean. Either way, the practice remains the same. Keep listening for the smallest clues, with instruments that trust only what many observations say together, and let the sky decide whether the beyond leaves fingerprints upon the within. He turns to the ultimate horizon and watches knowledge expand even as the reachable universe withdraws, because acceleration changes not only what can be seen, but what can ever be learned. The narrator begins with the present sky, and then leans forward in time. Today, the event horizon of cosmology is a shell that marks the farthest places from which a signal sent now can ever arrive. As the smooth energy that fills space continues its quiet push, more and more distant galaxies slide beyond that shell. Their last photons that were already on their way keep coming for a while, but new messages sent later will fail to cross the swelling sea. The deep future therefore resembles a gathering solitude. Bound structures remain themselves because gravity, electromagnetic forces and nuclear forces hold stars and planets tight against the outward swell. The local group of galaxies anchored by the Milky Way and the Great Spiral in Andromeda, and a retinue of smaller companions will complete its slow dance and merge into a single massive galaxy, long before the outer web fades. Within that island, stars will continue to form from whatever gas survives, the ongoing burn, and planetary systems will continue to spin around their suns. But beyond the island, the lamps will thin. Light from galaxies that are not gravitationally bound to the island will redden into wavelengths so long that no detector bound by practical limits can collect them, and then those sources will cease to send any new light at all as they pass beyond the event horizon. The narrator walks with calm care through the consequences of this drift. The cosmic microwave background is currently the oldest light anyone can observe, a near-perfect black body that arrives from the surface of the last scattering. As acceleration proceeds and space stretches further, the background cools and redshifts. Its brightest wavelength grows until it is longer than the scales that can be encompassed by future instruments in a noisy universe. In very distant ages, even a civilization with unimagined patience and technology may find that the background is no longer observable in practice, not because it is absent, but because it is stretched into a whisper weaker than any possible receiver can separate from local noise. The quiet photograph that now anchors cosmology will fade from the toolkit of future astronomers. The standard rulers and candles we use will also retreat. The acoustic preference frozen into the separations of galaxies will be impossible to measure once most galaxies beyond the island cannot be seen. The dimming of standard candles across vast depths will offer no leverage if the candles themselves cannot be observed. In that future, a careful scientist may still infer a slow local expansion by measuring how the orbits of very distant stars on the outskirts of the merged island respond to the changing geometry, but the grand evidence we now use will be gone. The narrator does not mourn this loss. He treats it as a feature of a universe that places horizons where time and geometry require them. He notes that something else will grow in clarity even as the sky empties. In a universe dominated by smooth energy, space-time tends toward a very simple form, at the largest scales a state in which expansion is exponential, and any leftover clumps become mere local details. This tendency is sometimes described as a cosmic smoothing that erases the memory of initial complexities. The boundary of knowledge therefore narrows in content but sharpens in form. A distant observer deep in this era will see only the local island of stars against a dark that grows darker. If that observer reconstructs history from available evidence, the story will be different from ours. There will be no map of the cosmic microwave background to anchor initial conditions No web of galaxies to reveal the acoustic ruler, no distant supernova to chart the late-time acceleration. Within the island, stellar archaeology and nuclear chronometers will still provide ages, and the behavior of gravity on small and intermediate scales will still be measurable. A correct inference of a late accelerating expansion might still be possible through delicate experiments, but the case will be more inferential, more local, more indirect. In this way, the ultimate horizon is not only a boundary in space, it is a boundary in method. The narrator considers black holes as microcosms of the same logic. Around a massive black hole there exists an event horizon that no signal can cross outward. Information about what falls in becomes in practice unreachable to the outside observer. In quantum theory, black holes radiate slowly, but the timescales for large holes are staggeringly long, far beyond the ages of stars. Whether that slow radiation fully returns the information that appears to have been lost is a deep question at the edge of current understanding, but the analogy stands horizons shield details while allowing broad laws to persist outside. The cosmological event horizon plays a similar role. What happens far beyond it cannot alter local experiments through direct signals, yet the presence of the horizon and the uniform energy that produces it shape the overall geometry in which those experiments sit. The narrator then traces the path of a single photon born in a remote galaxy today. If that galaxy is close enough that it remains within our event horizon, the photon will eventually arrive stretched in wavelength by the expanding space through which it travels. If that galaxy is beyond the horizon, the photon will never reach us no matter how long we wait. The notion that more time solves all problems fails when acceleration reigns. There is a limit to knowability that grows tighter as the future unfolds. He pauses to reflect on how the practice of science adapts within such limits. The correct response to an ultimate horizon is not despair, but focus. We measure what can be measured now across all messengers to infer what can be inferred robustly before the evidence thins. We write our methods clearly so that future observers living in a leaner sky can understand how these conclusions were reached when the cosmic microwave background still shone and the wide web still stretched across the night. Perhaps artifacts of our time transmitted across local ages will preserve the ancient maps long after the sky itself no longer supplies them. The narrator returns to the question that threads this work. What exists outside the edge of the universe in the sense of regions beyond our received news may be continuation or variety. But as the event horizon tightens, the ability to test either conclusion fades. At the same time, another kind of answer becomes surer. The overall future looks increasingly simple at the larger scales: exponential expansion isolation of bound islands, redshifting of ancient light, and a deepening quiet. Within the islands, complexity persists for a very long time, as stars cycle and planets turn. Far later the fuel thins and the night cools further. At every stage the horizon remains a rule, not a wall shaping what conversations are possible and what maps can be drawn. He does not end with finality because the discipline forbids it, but he acknowledges the dual motion that defines the ultimate horizon. Knowledge grows inward, clustering around reliable inferences that do not depend on access to the far field, while access to that far field shrinks outward, sealing away details that once were reachable. The more we learn now, the more we can leave behind for the ages when direct evidence is scarce. The narrator leaves the section with a calm, measured image. The universe is a theatre that expands its stage faster than any actor can cross it. The footlights that ring the far seats dim until they vanish beyond the curtain of acceleration. The players near the centre continue their lines within a local pool of light, and their script includes a record of what the whole theatre looked like when it was still fully lit. The ultimate horizon does not bring an ending. It brings a change in venue for inquiry from a universe rich in long baselines to one that must read its history from fossils and from laws that survive the dimming. What lies outside remains what it has always been, either more of the same or other domains forever beyond contact. What lies inside changes as the lights recede, and that change is itself part of the story we are telling, because the edge is not a cliff but a timeline, and we are moving along it. He turns to the question without end and holds it gently because the edge of the universe is not a place to be reached, but a way of thinking that refuses to stop. The narrator gathers what the sky allows without tying it into a knot. The faintest light shows a pattern of ripples nearly the same at all sizes, written when the young universe cools enough for photons to move freely and the fog clears. Those ripples and the quiet flatness of large-scale geometry suggest that an early burst stretches space-smoothing irregularities and lifting tiny quantum jitters into seeds for all later structure. The measured expansion, first slowing and then gently accelerating, says that a uniform energy pervades space today, pushing distant regions apart faster than any signal can cross. The horizon that encircles our received news therefore grows as time passes, yet the event horizon that limits future conversation draws in, sealing away more of what could have been learned if the push were not there. Between these limits, the practice of cosmology has found a way to be precise without pretending completeness. It uses acoustic rulers on the oldest sky and in the web of galaxies standard candles, whose dimming over distance tracks the growth of space weak lensing that traces the invisible scaffolding on which galaxies hang, and a slow widening catalogue of gravitational waves that carry news through every obstruction. These strands form a braid that holds firm when pulled, and in that firmness a discipline has grown that treats the night as a patient archive rather than a stage for grand declarations. The narrator walks along the margins where certainty thins and keeps the pace unhurried. There is the cold basin on the microwave sky that might be a natural dip in a single random realization, or a hint of a large underdense region along the line of sight, or a faint bruise from a meeting with another's domain. There are alignments and hemispheric tilts that appear and soften as maps are cleaned and methods are refined. There are whispers of a twist in polarization that could be a pane of cosmic glass, or a calibration ghost waiting to be exorcised by better cross-checks. There are gentle tensions between how quickly the nearby universe expands today and how the early sky would predict that rate under the simplest assumptions, tensions that may be the dust of measurement or the first scuff marks of new physics. Each anomaly raises a question that remains open without breaking what already works. He does not stack possibilities for spectacle. He places them one by one on a narrow shelf where patience can find them later. The narrator then looks beyond what can be sketched to what can only be framed. If inflation is a process that ends in patches while continuing elsewhere, then beyond our horizon there may be other domains' bubbles that complete their burst with slightly different initial tilts, or in more adventurous cases with slightly different values for a few constants that steer chemistry and stars. If higher dimensions exist, then our universe could be a brain floating in a larger space with other brains stacked in directions we cannot walk, and the phrase outside may include orthogonal corridors rather than further reaches along familiar axes. If space wraps, then the word beyond could mean again rather than farther, though present searches for repeating circles on the oldest sky push any wrapping scale far beyond our visible sphere. If nothing so elaborate is true, then the simplest continuation holds more filaments, more galaxies, more voids that extend indefinitely under the same rules we see here, with no edge in the sense of a boundary, only a horizon in the sense of a time-limited conversation. Each frame is a clean conditional, and the measurements we own today neither compel nor forbid anyone entirely, though they favour calm versions and disfavour loud ones. He brings the focus back to method because the question without end is answered to the extent that it can be by habits rather than by pronouncements. The habits are to deepen polarization maps until the smallest allowed curl or rotation either appears with the correct fingerprints or vanishes within even tighter bounds. To extend weak lensing surveys until the larger scale shear becomes a clean measure of how the web grows and whether gravity behaves exactly as expected across cosmic distances. To lengthen the reach of standard rulers and standard candles so that the history of expansion is traced without assuming a form. To widen the catalogue of gravitational waves until a background emerges, whose shape and sky pattern can speak about the earliest times or else confirm that astrophysical choirs alone fill the band. To refine spectroscopic clocks and quasar line comparisons, until any drift of constants either stands out coherently across many species and instruments or retreats below belief. In that program, the beyond becomes present as a set of small, decisive possibilities. The narrator keeps the tone level as he turns to the human position within this inquiry. We live in an era when the cosmic microwave background is still bright enough to be mapped, when far galaxies still fill the night with measurable structure, and when the event horizon has not yet sealed away most of what could ever have been seen. This is a fortunate temporal location not by design but by fact. It gives us a chance to write a record for future astronomers living within merged islands of stars when most of the sky has dimmed, and it gives us a chance to draw boundaries around what can never be known even in principle, and to do so without despair because the limits themselves are sources of clarity. The horizon is the shape of our question. It tells us what we mean by outside and what we must mean by evidence. It tells us that the universe is not a fruit with skin, but a history with a last page we cannot turn even though the story goes on. The narrator returns at last to the opening claim that the edge is not an edge. What exists outside the edge of the universe is either more of what the laws already predict, or a quiet variation secured by the same laws folded into deeper structures, and in either case the word outside marks a distance in time for messages rather than a distance in space for travellers. The answer is therefore not a picture but a method, a map that expands with observation, a set of tests that prune exuberant ideas, a language that keeps speculation tethered to stable anchors, and a willingness to let uncertainty remain where it belongs, not as a failure to be cured, but as a frontier to be described. He closes without sealing the door. The oldest light still cools, the web still grows and thins, the expansion still accelerates, instruments still sharpen, and the conversation with the night still changes as the night itself changes. We will either find small coherent deviations that point to other domains, hidden directions, or early contacts, or we will not, and the not will be a powerful statement that our patch is a faithful sample of a larger repeating calm. In both outcomes, the question continues to do its work. It trains observation upon the farthest signals, it binds theory to modest predictions, and it keeps wonder honest by asking for evidence even as it permits imagination. The edge approached with this steadiness becomes not a dare but a horizon on which the sky keeps writing. The writing is faint but legible to those who wait, and the story it spells is generous. No final pronouncement, no closing statement, only the ongoing exchange between what is measured and what is possible, and a night that remains large enough to contain both.